All right, everybody, good morning. Hope you all had a wonderful weekend. I know I did, watching the Patriots beat the Eagles, which was nerve-wracking as heck, but it is what it is. They got the W. And like I said, my dad was in Philadelphia. He almost got beat up by an Eagles fan, but that's, again, besides the point. But I am more excited to start our unit on adding and subtracting fractions. Now, as you've seen in the past, we've always had our unit goal. So for this unit, our unit goal is to use our knowledge about adding and subtracting fractions to study populations. Now, some of you may be thinking, how can we do this? Well, eventually what we're going to be doing is, at the end of the unit, we're going to do an activity where we're comparing the populations of the 7 biggest cities in the United States. One of them, I believe, is Los Angeles, or off the top of my head. 2 cities abroad. One of them being Budapest, one of them being Shanghai, China. And what we're doing is using our knowledge of adding and subtracting fractions and creating equivalent fractions to compare what fraction of the population of Shanghai and those other cities is made up of the 7 cities in the United States. That's exactly where we're heading. Throughout the unit, we're going to be self-reflecting and going through processes where we're determining if what we're learning is actually helping us in achieving our unit goal. And if we're not, we'll come together. You'll tell me, hey, this isn't working. Just tell me outright. It's perfectly fine. I'll self-reflect on my own teaching and say, well, this isn't working. We're not getting there. How can we reconvene and fix everything we need to fix? So again, that's our actual goal. And at the end of class today, after the worksheet, we'll come together. We'll reconvene and we'll determine if what we've learned today is actually helpful. So, in terms of adding and subtracting fractions, the first lesson is actually on, this would work, equivalent fractions. Now, equivalent fractions is actually a little bit of a review. We did some of this in the end of 4th grade and 5th grade, but it's important that you have a good foundation and are able to form different equivalent fractions using different methods and things like that. So, our agenda for today, intro to unit, kind of did that with unit goal. I'm going to do a do now on vocab, which is 2 words. It's important you know them. The brownie problem, which I think is a really good one. Brief mini lecture, about 15 minutes, and then a worksheet, and then we'll reconvene. So, our do now activity. By yourself, and without using any sort of technology, phones, tablets, laptops, etc., I would like you to come up with your own definitions or pictures for the following vocab words: equivalent and greatest common factor. I'll be asking for 1 volunteer for each vocab word to share their definition or picture, and then I will share my own definition, and we'll vote as a class what we want our class definitions to be. So I'll give you about 2 minutes to do that, and then we'll reconvene. Got about another minute here, and then we'll reconvene. So if you're just coming in, we're doing a do now activity. We're just defining 2 vocab words I have on the board without using technology, and we'll reconvene together, and we'll come up with our own class definitions. That's the plan for now. Okay, is everybody all set? Does anyone need any more time? It works for me. So, who would like to give their definition or picture for equivalent? Who would like to volunteer? Yeah, Taylor.
I wrote to have the same value, and I also drew a picture of a big equal sign.
Perfect. Have the same value. very similar to the definition I have. Does anyone have something similar to this that we like this definition? Works for me. How about greatest common factor?
The highest or largest number that's a divisor for two or more given numbers.
Perfect. Good. I like these definitions. They're very, very, very similar to the ones I have. I also like the equal sign here. Shows that we're thinking visually. One that I thought of for equivalent, I drew money. I thought of 4/4 of a dollar. That's something I represent it. It's important that we're able to visually see this as well as memorize the definitions. The definitions I have for equivalent is equal in value, which is to have the same value. And for greatest common factor, largest number that divides two separate numbers, or for two or more given numbers. These are actually perfect. I like these definitions. Are we good with these being our class definitions? Super. Works for me. So, why did I have you guys do this? Well, the importance of vocab and math is very, very critical because when we're getting into the nitty-gritty stuff in the end of the unit, in the middle of our unit, you're going to have to be able to justify your solutions using words like greatest common factor, equivalent. I didn't put numerator and denominator up there, but there's sort of an assumption that numerator and denominator is something we're very comfortable with and familiar with. So again, when we're justifying our solutions as we go along, these two vocab words are going to be critical. We're good to move on. So, the brownie problem. I like this one. It's very visual and it's going to segue into our actual mini lecture. So, Tom makes brownies in two pans of the same size. He cuts the pans in the following ways. Namely, pan A is cut into two large rectangles cut in half, and pan B is cut into a larger rectangle but with 8 pieces. Tom gives one brownie from pan A to Andrew and keeps 4 brownies from pan B for himself. Andrew thinks this isn't fair since he got 1 brownie and Tom got 4. Tom, on the other hand, thinks it's fair. So what I want you guys to do is, with the people that are around you, is determine who you agree with, Tom or Andrew, and why, and using this word as our main source of justification. I'll give you about 2 to 3 minutes to work with your group mates, and we'll come back together and we'll determine who's right and why. So 2 to 3 minutes on this.
So they're equivalent. But as a kid, I was still nervous because 4 is more than 1.
I like the discussion. That sounds good. From the silence I hear, it sounds like you guys are all set with this. So, who is right and why? Who would like to give an explanation?
Jonah and I think that Tom is right because 1/2 of the pan, 1 brownie from pan A, is the same as 4 out of 8 brownies from pan B, which also equals 1/2. So they got the same amount. So it's fair.
So you're saying that the area or the number of brownies here, in terms of area, is going to be equivalent to the 1 brownie we have here.
Yes.
Okay, perfect. I like that. Does anyone come at the solution a different way or approach it another way?
Well, what we did was we shaded how much each person got. We colored it in, and then we realized that we colored in pretty much the same thing, pan A and pan B. So it looked like it was equivalent area.
Okay. Yeah, I like that. The whole shading is actually going to segue into what we're doing next, but I like the shading method in that way. Because you shade here, because I mean, obviously for us it's easy to tell, but sometimes it's hard to tell because this might look like it's a little smaller, and this might look it's a lot bigger. But if you shade it in and you do it that way, the shading is actually the same. So we recognize the area is the same, and in terms of fractions that are represented are the same. So yes, Tom is right, because he gives half of his pan away, and then he would get half of his pan B from Andrew. So Andrew is just terribly wrong, unfortunately. But you'll learn that stuff. We'll be learning the rest of that stuff as we go along. And this is actually going to segue into our first part of the mini lecture on area models. So what is the goal for area models? First of all, has anyone seen area models before? Has anyone had any prior experience with this? That's fine. It's something we can all learn. I think it's really, really useful, especially for anyone who appreciates visual things. This is something that's very visually appealing, as judged by the colors that are there. So our goal is to represent fractions as shaded sections of area. Now, what we did on the Brownie problem was actually really cool because we saw that Talon said we shaded a section of area. And we're doing the same thing here. We're shading sections of area and manipulating given areas to represent fractions. So for our first example, we're just going to jump right into it and we're going to kind of explain as we go along. Create an area model for 1/2 and use the area model to find an equivalent fraction. Now, I've kind of just given the answer away, but we can work together on it. So, what do we notice about the area model here, generally? What do we notice about it?
You colored in the same amount in
Okay.
each circle.
Okay, yep, they colored in the same amount in each circle. That's exactly the point, because we're trying to get the shading to stay the same, but have it be made up of smaller pieces. One of the things I also notice here is that we have a common area, circle. For our purposes, we'll use circles and rectangles to represent areas. Like for the Brownie problem, big rectangles. If you think in terms of like cookies or pizza, you do it that way. But for our purposes, we use circles for this example. Now, how many pieces is this circle cut into? First one. 2. Can anyone tell me why? Why do you think it happens? Well, how about because there's a 2 in the denominator of a fraction we're trying to represent? That's something that's important to know. That the number of sections that you're cutting your area into is based on the number in the denominator of our fraction. So namely, if this was 4, we cut it into 4 sections like we see in the second example. If it was 8 sections, so on and so forth. So as we go here, the first thing we want to do is we want to cut our area into 2 equal area sections, making sure to cut it, you either cut it horizontally like this, vertically, diagonally, as long as the 2 sections you have are equal in area. Okay, now we notice that like Talon said, one of the sections is shaded. Why would that be shaded? What's the importance of the shading then? What do we think? Exactly. Perfect. You shade in, the number of sections you shade in corresponds to the number in the numerator of our fraction we're trying to represent, namely 1/2. So if this was, if we did something where it was 2 3/4, we shade in 3 out of 4 sections, 4/5, 4 out of 5 sections, and so on and so forth. So do we understand how we can represent our original fraction using an area model? Do we understand how we come to that conclusion? Perfect. So this is our 1 fraction. We want to create an equivalent fraction that has the same value, but the numerator and denominator are different. I've actually given you some area models that come up with equivalent fractions. What do they do to this original area model? How do they manipulate it to get it so that it's made up of smaller pieces, but the area shaded stays the same? What do they do? Well,
They divide the sections again.
What you're actually doing is just making it so this area is made up of smaller pieces. Essentially what you're doing is cutting up your area in smaller pieces while leaving the shaded area alone, so that the value of the area that's here, as shaded, stays the same, but it's made up of smaller pieces. It's almost as if, like in the original, we had a person who was 50 feet tall standing here. And next to them, we had 10 people who were 5 feet tall standing on each other's shoulders. The height's the same, and in this case, the area is the same, but we're made up of smaller pieces with the 10 people versus the 1 giant, even though it seems rather impractical in a room that's maybe 15 feet tall, but alas, it works. And again, we can continue to do this and make it smaller and smaller and smaller, while we notice the shaded area never changes. The colors change, but the shaded area never changes. It's just made up of smaller pieces. So do we think that as we go along, we'd be able to continue to do this? We'd be able to represent other fractions using this method. I want to do one example with you guys, or have you guys help me out for an example. And we're going to try and find an equivalent fraction for, let's do 1/4. How's that sound? 1/4. So, What do we want to do first? How do we want to represent our area? What shape do we want to go with?
Rectangle.
Perfect. Like that. Terrible rectangle, but we'll do. So how many pieces do we split this into based on the numbers that are there?
4.
Mm-hmm. Yeah, those are equal enough, sure. How many pieces do I shade in? Mm-hmm. Does anyone have a preference on which one I shade in?
Second one.
Okay, perfect. Okay, how do we want to manipulate this? How do we want to cut this area so it's made of smaller pieces?
This way.
Horizontally. Beautiful. Now, before we had 4 large rectangles. How many rectangles do we have now?
8.
Mm-hmm. So that 8 becomes our denominator. How many are shaded in?
2.
2. Beautiful. So we end up with 2 out of 8 rectangles shaded in. Because the area didn't change, it's made of smaller pieces, we now have that 2/8 and 1/4 are indeed equivalent fractions. So, who likes this method? Who thinks they could recreate this and use it again? Who likes the visuality of it? I like the enthusiasm, too. I really appreciate that. Okay, good. Am I good to move on? Are we clear with everything that we're doing in this method? Works for me. Number lines. Who doesn't love number lines? So, how many of you worked with number lines before? I know I have in elementary school, keeping track of the days we had left at school. I was counting down to 180 and waiting for it all to be over. But I like it. I like number lines. So, brief review. This is, you can raise your hand if you know right off the bat. What fraction does this point on the number line represent? What does that represent for us? Mm-hmm. Now, how'd you get there?
Well, from 0 to 1, it's divided into 4 spaces.
Mm-hmm.
And you go 3 spaces.
Yep, exactly. Because again, like Kylie just said, it's from 0 to 1, there's 4 spaces. The dot mark, or the dot here, is on the 3rd out of 4 spaces, where tick marks line up the column. So that's 3 out of 4 because the number line goes from 0 to 1. Good. What about the second one? What is this number line representing in terms of a fraction? What do we see? I know it's tiny, right? I apologize. Yeah, I apologize for being tiny. I can see, I'll help. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total. So, what fraction is represented by that number line there?
9, 12.
And we got there because, same thing Kylie had mentioned, we counted the number of tick marks or spaces from here to 1, bless you, and whatever number the dot is on, so for us it'd be 9 out of 12 possible. So, we put the number lines on top of one another, what do we notice? What do we see?
The dots are in the same place.
What do you think that means for us?
The fractions are equivalent.
Exactly. Perfect. Figured it out. So, when we are using number lines to find equivalent fractions, we're actually manipulating our original number line to create a new one, but the dot stays the same. It's like with the area models, where we had the area stayed the same, it was just made of smaller pieces. But in our case, the number line is going to be made of more spaces here. So originally we had a number line that looked something like this. We went 0, 1, 2, 3, 4. How could I manipulate this number line, which represents 3/4, to look like 9/12? What would I do? Add more lines. And the key point is you have to add them equally across the sections you have here. Because if I wanted to add 1 here, 2 here, 1, 2, 3 here, it wouldn't work. What we have to do is we have to add them equally across the number line. And for our case, we added, I believe it was 2 per section. So 2 here, 2 here, 2 here. So now, these are horrible lines, but we have from 0 to 1, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 here, 10, 11, 12. So, this fraction represented here is 9/12. But remember, the dot didn't move. It stayed in the same place. So for us, that means what? If we started out with 3/4, ended up at 9/12, the dot didn't move. What does that mean for us? Perfect. They are equivalent fractions. And now there's a different way to do this. You can approach it where if you want to create your original number line, recreate it on the bottom, stack them, and then manipulate your original number line, you can get to a point where you see the number line stacked like that, right? But if you want to do it this way directly, where you see it like that, we're able to have our original number line, manipulate it, and create an equivalent fraction from it. So do we think we can recreate this or do something similar to this? Again, this is something that's in between visual and more algorithmic. I like this method. I think it's something that you really can use if you don't like the area models, you don't like the next method we're going to go into, something I think we can work through together. I want to do one more example with you guys just to make sure we're hitting home with this. Does anyone have a particular fraction in mind they want to represent as a number line? If not, I have one. It's perfectly fine, but
1/2.
sure. Okay, we have a fraction here, representing the number line representing 1/2. How could I manipulate that number line so that the dot stays the same in the same place rather, but the number line changes? What can I do?
Put 4 tick marks in between each of those. The
Okay,
ones that
I
are
like that. Okay, so what Sam did was good. She made sure to put the tick marks equally across my number line. So how many tick marks do we have now between 0 and 1? 10. Good. So that number becomes our denominator of our fraction. What number line, or what? Well, that sounds terrible. What line is this on in terms of the number of lines we have here? Perfect. So we get that 1/2 and 5/10 are equivalent. Again, we make sure that this dot never moves. That's the important part. Because if it moves all over the place, it's not the equivalent fraction. As long as we're doing this equally, 4 in here, 4 in here, creates a little smiley face, makes me happy, works out perfectly. So, if you like this method, we can use it, right? Good, I like that. So the next method, if you guys are all set, we can move on, is actually something we've been doing the entire time. So, oh, why did I do that? Come on. So, oh, what are you doing? Perfect. So, multiplication and division method. Going back to the brownie problem in the beginning we saw, we recognized that 1/2 and 4/8 were indeed equivalent fractions. Oh, I forgot the symbol for equivalency. Whatever. Sure, call it that. What do we notice about the numerator and denominator of our fractions here? What do we notice? How does this change 1/2 to 4/8? What do we notice?
multiply the top and the bottom by 4.
Perfect. So what we're doing here is multiplying by 4 over 4 to get us 4/8. Now, why can we do this? Anyone know why we're able to do this? Why can we multiply by 4 over 4 and the value stays the same? Exactly. This is just literally just 1. But a common misconception a lot of students have is when I say, oh, multiply by 4 over 4, they just multiply straight across. They multiply 4 times 1. They forget about the denominator. They go, oh, that's not important. When I do multiplication of fractions, I multiply straight across. They forget about this. That's so important. Because if I just multiply 1/2 by 4, I get 2. And 2 and 4/8 are not equivalent fractions at all. We're getting a number that is not even close to what we want. But, so, in terms of division for this, I'm sorry, brain fart. In terms of division, there's nothing we do to make this smaller, because the 1 here in the denominator, or the numerator rather. In terms of division is going to be one you're going to use your greatest common factors for. Like, I'll get to the example at the end, but if we're doing something where it's like, so this is example 1. So we're doing, I don't know. Say we're doing 5/10, right? 5/10. How can we use division and multiplication to get equivalent fractions? What can we do? How can we manipulate this?
Would you divide by 5?
Mm-hmm. Question mark, wow. Yeah, you'd be dividing by 5. So instead of multiplying, you're dividing by 5 over 5. Now, how did you get this? How did you get the 5s?
Because I tried to make the 5 into a 1.
Good. Just one. But 5 here and the 5 here, what is that in terms of our 5 and 10? What is that? You didn't vocab
The
today.
greatest
Greatest
common factor.
common factor, exactly, perfect. So when we're dividing, when we're doing the division part of this, what we want to do is we want to, if we can find the greatest common factor between our two numbers, do it that way, or pulling out, for our, in this case, 5 and 5 in the numerator and denominator. Sometimes you can't, and there's just no chance of making it smaller with like 1/2. Those are the times where the greatest common factor is, again, 1. So sometimes you just have to pull out common factors, like we have even numbers like 2 and things like that. So for, I guess we'll go back to another example we did prior. We had 3/4. Now we know that 9/12 is 1. How do we find another one? Who can tell me another equivalent fraction for 3/4?
30 over 40.
Okay, I like that. How'd you get there?
I multiplied by 10 over 10.
Good, good. 10 over 10, that's kind of perfect. Again, you can get infinitely many equivalent fractions using multiplication. Now, for our purposes, we don't want to make gigantic numbers. Like, that's cool. But if I want to do, I don't know, 300, just keep going, et cetera, et cetera, et cetera, et cetera, et cetera. You can get to that point. We don't want to do that. We want to keep things as small and concise as possible. Because that's what we like doing in math. We want to work smarter, not harder. Where we're able to do these things efficiently and effectively. That's our goal. So, what have we done in the 3 strategies? I want to review if everyone's cool with this. Are we cool with the multiplication, how we do it, how we apply it? And again, I want to make sure this is important. What you do in the numerator, you do in the denominator. That is so critically important. Okay, and if you don't do it, you're going to get wacky numbers that don't make any sense. Because if I pull out a 5 here and not here, I'm going to get 1 over 10. And not equivalent fraction. It's not close. Okay, so now that we're good with that, what have we done? Well, we've gone over area models, where we're representing fractions as sections of shaded area. And we're manipulating that area to make it smaller. Like I said, the giant example was when the giant was 50 feet tall versus 10 people who are 5 feet tall. We went into number lines, where we're essentially creating a number line to represent a fraction. Going from that number line to a new one by adding tick marks equally across that number line. And then, as we said before, if the dot doesn't move, it's the same fraction. It's this equivalent fraction represented a different way. And then multiplication division, my favorite. We've been doing it all along. I'm sure some of you have recognized it, but we had to do the other methods to get to this point. But we're doing something very algorithmic and quick. As you recognize, okay, we can multiply by 4 over 4. We can multiply by 5 over 5. And again, I know I said it before, I just want to stress the importance of it. What you do here in the numerator, you must do in the denominator. I know I sound kind of like a robot, but it's very, very important that you're able to understand this. So, now that we have done that, we've gone through our mini lecture into the Brownie, from the Brownie problem to the mini lecture. I have a fun worksheet for you all to do.